There's a sequence of just 5 bytes that can infect a Commodore 64. It's resistant to reset, and it can take several minutes after cutting the power before the computer can return back to normal. Stay tuned and I'll show you how it works, as well as some hardware and software mods that can stop it. Hey, I'm Trevor Makes, and one of my favorite things about programming for 8-bit computers is their complete transparency and lack of security features. There's no privilege levels, no protected memory segments. Basically, any program is free to modify any part of memory, from system variables to hardware registers, and discovering how it all fits together is just part of learning how to program the computer. Obviously, this approach wouldn't work for modern computers, since it turns out that security is kind of important when you have hundreds of background processes, software updates, browser tabs, all on top of a 24/7 internet connection. Still, I think there's real educational value in a computer that's simple enough that it can be understood just by disassembling a few dozen lines of code or by looking through a hardware schematic. And that's one of the reasons why I've been really excited to create a series of videos about the Commodore 64. But today we'll be taking a look at an example of where the lack of security concerns created a rather annoying software exploit. So notice how... Oh, it's already covered up. Let me reset it again. Notice how the free basic bytes here was reading something other than it usually reads. While I was researching my previous video on the Commodore 64's reset circuit, I came across an interesting hardware mod called the Unstoppable Reset, which has to do with an exploit that allows a program to bypass attempts to reset or restore the computer. This behavior was really intended for expansion cartridges that are supposed to boot when the system powers on. And the way they did this was by placing a special 5-byte signature in the external ROM chip that the computer would check for when it starts up. But it's possible to trick the computer into seeing this signature even when there's no cartridge present. To understand why, we need to take a closer look at the Commodore 64's memory architecture. See, the computer gets its name from the fact that it has 64K, or kilobytes, of usable RAM, enough to fill up the computer's entire 16-bit address space. But on top of that, there's also 20K of built-in ROM, up to 16K of expansion ROM, plus another 4K set aside for video memory and I/O registers. What makes this possible is a trick called bank switching, where a given range of addresses may map to 2 or more different memory banks, and deciding which one the computer actually means to talk to is decided by some separate bank select logic. On the C64, the built-in ROMs and I/O registers are banked in and out by some extra logic that's built into the CPU itself. But it gets a little messy when the expansion ROM comes into play. The cartridge port has 2 additional bank select lines, set by jumpers on the cartridge itself, that can make up to 2 external 8K ROMs available. These bank select lines are fed to the address decoder, but they completely bypass the CPU. So when the computer reads from the block starting at address hex 8000, which can be either internal RAM or expansion ROM, it turns out that the CPU doesn't actually know which one it's looking at. And to make matters worse, this is exactly where that 5-byte signature is supposed to be. So if you simply copy that 5-byte signature into RAM, any attempt to reset or restore the computer will get trapped by the fake reset code. Let's take a look at a simple example that demonstrates how the 5-byte signature is supposed to work. So this is 6502 assembly code written for a Commodore 64 focus tool called KickAssembler. The code can be found on GitHub, and the link is in the description down below. Now, the most important part is the signature, which starts at address hex 8000. The 5-byte signature is actually not the first 5 bytes. So the first 2 bytes are the reset vector, the 2-byte pointer to the code that executes at reset. And then the next 2 bytes after that are the restore vector, which is the code that runs whenever you press the restore key. And then, of course, the next 5 bytes is the magic signature, which is actually CBM80 in ASCII code. This is what the computer checks for its startup, and if it sees it, that's when it jumps to this reset vector. And likewise, whenever the restore key is pressed, it actually checks to see if this signature is present in RAM, and if so, it goes ahead and calls this restore vector. Now, to keep this demo simple, I basically just made both of these functions print out a string and then go into an infinite loop. For reset, it prints trapped reset. For restore, it prints trapped restore. And there's also these 4 bytes here. These are just control characters that clear the screen and change the text color to white, basically. So just for a quick demonstration, I'll load the code up in the emulator. So if we press the restore key, we get the message trapped restore. And if we try to reset, we get trapped reset. Once this code takes over, the only way to get the computer back to normal is to switch the power off and wait for the memory to discharge. In my case, it only seems to take a few seconds to recover, but on some systems with Fujitsu brand DRAM, it can apparently take up to 15 minutes. Not the end of the world, but still pretty annoying. And that's where the unstoppable reset circuit comes in. So let's go ahead and build one so we can see how it works. Okay, so I have everything here to build this unstoppable reset circuit on this breadboard. And the way I'm going to do that is by making use of this cartridge adapter board that I had previously used for making a dead test cartridge. Now, the reason I want to do that is because in this circuit here, we make use of the XROM and reset lines as well as ground. And this cartridge adapter board very conveniently has XROM, ground, and reset, which I've already hooked this yellow jumper wire up to. And so essentially what this circuit does is when you press the reset switch, it's going to pull the reset line down low, but it's also going to pull the XROM line down at the same time. And so after the switch is released, it will slowly discharge these capacitors, which will release these 2 lines back high. And you can see here, this 12K resistor is used so that this XROM line is released a little bit slower than the reset line. So the idea is that the reset line should go high first, followed just a little bit later by the XROM line. Now the XROM line, what this does is this will switch in the external ROM. Specifically the one that is located at address 8000, where that reset signature should be. Now, because I don't actually have a ROM chip plugged in anymore, what that means is when the XROM line is pulled low, the computer is going to see just junk basically. It won't be reading from RAM, it'll be reading from this, but this isn't hooked up to anything. So the lines that it's reading will just be floating. And because this circuit is designed to keep the XROM line pulled low a little bit longer than reset, the idea is that the computer should start running through the reset code, and just during that part when it checks for the signature, that's when the RAM should be switched out and it should just see junk. So that's the whole principle of how the circuit is supposed to work. Anyway, let's go ahead and build it. So first off, I'll plug in the ground here, and I will run ground to the bottom leg of this switch here. Then I'm going to run a jumper up here for the 10K resistor, and I will run the diode down here for the 12K resistor. So I'll do the jumper first. So I'll put this 10K resistor up here. Which is like this. Okay, and that puts the 10K resistor and the capacitor in parallel. And that goes to the reset line. So I'll plug in the yellow jumper there. Okay, so that's the top of the circuit done. Then I need this diode here. And so we connect the negative leg of the diode to the same leg of the reset switch that the other resistor is connected to. Okay, there we go. And we'll connect the, okay, there's our 12K resistor. And the last capacitor needs to go in parallel with the resistor with the negative leg towards the diode. Go ahead and put that like so. And finally, we connect the XROM line of the cartridge to the resistor and capacitor over here. And there we go. There's the unstoppable reset circuit. So I'm going to go ahead and plug this into the Commodore 64, and we'll load up some of those programs and give it a try. Okay, so I've got my unstoppable reset circuit hooked up to the cartridge port, and I've got my SD2 IEC drive hooked up so that we can load in the example program. Let's go ahead and give this a try. Load simple.prg, 8, 1. We do need the comma 1 here since this is a machine language program. It loads directly into address 8000. Okay, and we don't need to run. Now if we press the restore key, got to press it really hard. I'm going to talk about the restore key in a later video because it's actually due to a hardware bug on the same 556 timer from my previous video. Anyway, if we hit the reset switch, trapped reset. Well, that's no good, but what about the unstoppable reset? Let's give it a try. And so there we have it. The unstoppable reset is unstoppable. Just for fun, let's take a look at a more advanced example that I wrote specifically for this video. This time showing how it could be used to inject code into the otherwise normal boot process. In this case, I made it pretty obvious by changing the font color and then filling the screen with pop-up boxes. But a more malicious program might take this opportunity to silently hook itself into the operating system. This example is a lot longer, so I'm just going to focus specifically on the part that has to do with reset and restore. And if you'd like to take a look at the full code, you can find it at the GitHub link in the description below. So now if we take a look at the reset and restore functions, we can see that there's now a bunch of these jump subroutine calls to addresses that are up in the range of the kernel ROM. So this code is actually copied from the computer's real reset function, which is located at address FCE2 in the kernel ROM. This address can be found in the vector FFFC, which is the 6502's reset vector. And the first really interesting part for us is these 3 lines here. So this jump subroutine FD02, this is the actual function that checks for the CBM80 signature. And so if that signature is not found, we skip and we continue on with the rest of the code. But if the signature is found, it will immediately do an indirect jump to the address located at hex 8000, which, as I discussed in the previous example, is the location of the auto start reset vector. So if we wanted to make the computer start up completely as normal, what we could do is we could set that vector at hex 8000 to point to this address FCEF, and then it would just basically continue on with the rest of the reset function as normal. Now, the problem is if we wanted to do something sneaky in the boot process, we couldn't just do that first and then jump to address FCEF. Because if we look at these function calls here, these are responsible for basically resetting everything. So essentially, if we wanted to do something sneaky like mess with the kernel vectors or mess around with the settings on the peripheral chips, we would actually want to do it right here, either before or after the interrupt mask is cleared, and obviously before the jump to the basic code. And so the easy way to do that is instead of jumping to this address FCEF, we just copy paste all of this code here into our own reset routine. And that's exactly what I've done here. So here's that code copy pasted from before, followed by a jump to our inject subroutine, and then finally followed up with the clear interrupt mask and jump to the basic cold start. So let's take a quick look at the inject subroutine. So the first thing that I do is change the free top and memsize system variables. What these do is they set the highest address that basic code is allowed to touch. This isn't completely necessary, but it's just a good precaution to take. The next thing I do is I change the default text color to white, which is very simple. You just write the color that you want to address 286. And then the really sneaky part is here, where I change the operating system's break handler and interrupt request handler. Now, the first part here, the break handler, I'll talk about that in a minute, but it's really the interrupt request handler that's doing the heavy lifting here. This is where I hook into the code that creates the pop-up windows. Basically what happens is the computer fires an interrupt request 60 times per second, once per video frame. And any code that you would basically like to run in the background, kind of like a background process, can be hooked into the normal interrupt handler. So this just allows the code that creates the pop-up windows to run periodically and decide if it's time to create a new pop-up window or not. Anyway, moving on to the restore code, I basically did the same thing. I went and found the non-maskable interrupt handler, which is located at address FE43. Again, the interesting bit for us is right here. Here's the same call to that function at FD02 that checks for the CBM80 signature. And so if the address is found, we make an indirect jump to the address stored at address 8002. And otherwise, it continues on to scan the keyboard, check if the stop key is pressed, and if so, then it goes forward with a basic warm start. So one thing that's kind of interesting to note, if the CBM80 signature is present, it will immediately jump there when you press the restore key. Whereas normally if you want to get an interrupt, you have to press the stop key first and then the restore key. So anyway, we do the same process as before. We just take this code here and we copy paste. And that's exactly what we have here. And so when the restore key is pressed, we scan the keyboard, and if the stop key is not actually pressed, we just continue on with the normal NMI, kind of ignore it. And that's because the non-maskable interrupt is also used for handling one of the timer chips. But anyway, if we do find that the stop key is pressed, that's where we have the rest of the copy-pasted warm start code. But before jumping to the basic warm start, we again call our inject subroutine to hook into the interrupt request to create our pop-up windows. And so there's also the CPU break handler. This is the code that runs whenever the CPU encounters a break instruction, which is opcode 00. So normally that CPU break handler would jump here in the kernel to reset everything and do a basic warm start. But I made sure to redirect it here into our code so that we can make sure to call inject right before the basic warm start. And so that covers all three entry points into the basic interpreter. This one is a basic program, so we load it with -8 and then type run. And immediately we see the text color is changed to white and we start getting these pop-up boxes. Now, we actually still have control of the computer, so we could type in, let's see if I can do it before we lose. I don't think I'm gonna get it in time. Oh yeah, I lost it already. Oh dear. Can't type fast enough. Okay, what if I stop restore? Let's try and type something in real quick. I think I got it. There we go. So we still kind of have control of the computer and we can type in basic code and run basic code, but yeah. And obviously run stop restore doesn't work. The reset switch doesn't work. Notice how, let me reset again. So notice how, oh, it's already covered up. Let me reset it again. Notice how the free basic bytes here is reading something other, was reading something other than it usually reads. Oh God, look at the pop-ups go. Okay, let's give the unstoppable reset a try. There we go, it works. Now, I probably won't go so far as to actually build one of these and install it inside my Commodore 64 because this isn't really something that comes up very often. And in my case, this Commodore 64 and my other one, they both clear out memory pretty quickly when the power is cycled off for just a few seconds. So I just don't really see any need to actually have a physical version of this circuit, but I suppose it could be kind of cool to have like an external cartridge or something that you can plug in that does this. Anyway, that's it for this video. If you enjoyed it, please give a like and subscribe. Thanks for watching, and I'll see you next time.
Are you keeping up?